could sometimes be an acceptable alternative. But it's critical to note the motion is changing when the force is unbalanced. If everything's balanced, then the force is not going to. Say it again. If everything's balanced, then the motion is going to be constant in terms of its velocity. Okay, so unbalanced forces cause acceleration. Questions about that? Good. So I thwacked the puck. It moved. Audrey, what happened then? You said? It's friction causing it to do what? Can you tell me what friction is? A force. Good. Can you define it or no? Okay. Anyone want to take a stab at defining friction? No, nobody? Not brave? A force that, what do you think we should put there? A force that what?
Involves contact.
Contact between what?
Between the object and the surface.
Okay, so it's going to be two surfaces. I'm not going to write that. I think that's implied maybe. But what's that contact do? What?
Force that reduces acceleration.
Reduces acceleration. Well, it reduces velocity. Yeah, maybe not acceleration. It's going to cause acceleration. So force that reduces velocity. Okay. I mean, that's not incorrect, but I like to use a different word. Looking for an O word here.
Opposes.
Ooh. Force that opposes what? Motion. Or, what do you think, or else, besides force that opposes motion, what else do we think of friction happening? Does friction only happen when something's moving?
Movement.
Well, that's the same thing as motion. What if I'm pushing this book and it doesn't move? Is there friction?
No.
Or other force.
Or keep something.
I'm going to say it opposes motion or intended motion. So that's what the book there, I'm trying to make it move. It's intending to move, but there's something stopping it. And that would be friction trying to keep it in place. So it's the force that opposes motion or intended motion. So I would focus here on two words, and I'll answer your question there. I focus on just the fact that it opposes motion, and then this is kind of a new idea, maybe it also opposes intended motion. So if this puck is sliding that way, which way is the friction pointing? The other way. Good. So the puck, so this is the case now where this happened a lot in this chapter more than probably the first two chapters. A lot of you, since the time you were probably 3 or 4, started developing concepts of the world in your head that were wrong. Because you saw the world happening and you thought, oh, that's probably the case. And other people that have tried to learn stuff have also a lot of misconceptions in this stuff. And so you may have been taught the wrong thing by your elementary teachers or by your parents or by TV. And so we have to kind of break those down. So remember that when we define laws, like here we're saying friction always opposes motion. You might be doing a problem and you really, if you know this puck is moving to your right and something's telling you, I think friction's going to point right for some reason, don't draw that arrow, right? We know friction has to oppose motion. Even if this thing, that might happen here, this puck might be speeding up going that way, and you might want to think friction's speeding the puck up for some reason. Remember, friction always opposes motion. So the point I guess I'm trying to make is that in this chapter especially, let the laws of physics govern what you think. Isaac Newton was a smart guy. He's been dead for 400 years. He wasn't that smart, but he was smart enough to figure all this stuff out. He's probably right, and we're probably wrong. So let's make sure we put his ideas first. Blah, blah, blah. And if I'm pushing this book that way, and it's not moving, which way would I have to draw the friction arrow? Good, because the book wants to go right to your left, but we point the friction arrow to the right. There.
Why would that not be normal force? The book pushing against you.
Because I could also push like that, right? And that's not a rectangle anymore.
Oh. So normal force.
The word normal means perpendicular. So the normal force is always perpendicular.
But isn't the book also always a certain force back on you when you push it?
Oh yeah, but that's not the force I'm talking about. There's definitely if I touch this book, the book.
No, but I mean, like when you're trying to push it, it didn't move. I thought there was like a normal force.
There is definitely a normal force on me, but not when the book isn't moving.
Okay.
Because only the forces on, this is being a little more advanced, but only the forces on the book affect the book's motion. So I can push the book, and after the truth, the book pushes back on me, but that force The second force there affects my motion, not the book's.
Okay.
The force of friction on the book from the desk is what affects the book's motion. Kind of like if I kick this desk, my foot hurts afterwards, but the desk hit me back. But it didn't affect the desk move, what it did to me. Good question. Anything else right now? Woo! All right. So friction is going to oppose motion or intended motion. Good kind. What are we, 37 here? Is that right? 41? Oh, good. 20. All right. Airplane. All right. I need someone to help me out back there.
I got you.
Now, Brian, watch. Don't step on the ball. You can tap with your foot if you want, but don't step on the top of it.
You guys play soccer.
All right. Got it? Okay. I'm going to push this puck. I want you to watch the puck's motion in between kind of me or Brian. Don't watch us touching it, but watch the motion between me and Brian. I'm trying to describe it. I'm going to push it to you, you're going to do it back, we're going to do it one more time, and we're going to stop, okay?
Step on it.
So how would you describe the puck's motion between Brian and I? Constant velocity, very good. Were there any forces acting on the puck between, not when we're touching, but between Brian? Were there any forces acting on the puck? Gravity, good. Anything else? Or we'll call it still the normal force, essentially here. Because if there weren't a balancing force, that puck would have broken through the earth and gone to the fireball of death. And so there has to be a force keeping the puck from doing that. And so that we'll call it the normal force. Maybe it's the applied force from the air. It doesn't really matter right now what we call that force, as long as we know that it's balanced between the two, right? Would there be any difference in the force diagram for the puck moving at a constant velocity versus the puck when it was sitting still?
No.
No. And that's kind of the point. If I go back up on this little thing here to the earlier drawing we did, this diagram here, when the puck was stationary, would be exactly the same as the diagram for the puck going across the floor. In both cases, there's zero acceleration. And so all the forces are balanced. Agreed? Okay. Because again, we're ignoring friction and air resistance because we have this friction of air and we're on vessel vacuum. And after we push it. Okay. So we can make one more kind of claim here before we go. And that would be the following. Object in motion. In motion remains in constant velocity motion. That's a key point here. Constant velocity motion until what do you think? Until acted on by an outside force. Now I have an issue with that sentence. What's my issue, do you think? What's wrong with that word, do you think? What's that?
Not an outside force.
It's different? Okay, well, my problem is I think really all forces, other than like electrons, are outside forces, right? Gravity, normal, applied, all are outside the puck. So really outside is really too vague. What words should be there, do you think? Not different necessarily. Yes, sir? Inertia force. No. What's that?
Like instead of like acted on by inertia.
Inertia can't act on anything. It's a property of a material. It's a good guess, though. Brian?
All three.
No. Matt?
Opposing?
No. Yeah?
Unbalanced.
Unbalanced. Look at this guy. Unbalanced force. Remember, we're trying to talk about what causes acceleration. Unbalanced. And so maybe the force will be opposing, but maybe it'll be helping also, right? And so anything else. But unbalanced, that did not come up very well, is the word we want to use there. Unbalanced force causes acceleration. If you learn nothing else, can't put your arm tonight, unbalanced force causes acceleration. Don't really tattoo yourself. I'll get in trouble. Good stuff. All right, we'll do one more thing real faster. How, we got 2 minutes. I'm going to push this puck. How, if I want the puck to turn left or your right, what would I have to do to it? Push it right. You Yeah, from there. You do that? I'm gonna slide this to you. Nice. Brian made the catch. Now, you might need to catch it if she misses. Very likely. Okay.
Over there, once more.
I'm gonna slide it right to you. You're gonna have it right towards
Okay.
Christine, right? Now, question for you real fast. Do you think the puck's gonna go towards Christine or towards Jay? Let's find out.
Christine.
Okay, you didn't see it. The puck went a little bit this way towards Jackie. Why did it do that? Still have what do we call that?
Greater initial force.
Inertia. Still has inertia going towards the back wall. So even though Julia gave it some force going this way, still had the initial force towards the back wall, ends up veering off at a diagonal. While it's going towards Kelsey, what is it moving at a constant velocity or is it accelerating after Julia pushes it?
Accelerate.
Constant velocity, only normal force and gravity act on it after it leaves your hand. While she's touching it, it's accelerating. After it touches it, it's not. Homework 131, 1 through 10. Several questions. You can read the book. Don't just write the word gravity. Like actually write out like hey, what a guy.
Let's see, I'm right. I never said you were wrong.
Oh, good. There's like one air particle. There's like one air particle every 3 meters. Very, very small. Which air is probably not enough. There's one air particle every 3 meters. Alright, and then whenever I number with your partner, there's a thing is a perfect vacuum.
On Thursday because it's
But so there are some parts that are really spread out. The point, we obviously can't. Michael. Right now, I would say no, because this table is level. Now, if the table weren't level, I put on a ramp, like passing a ramp. Some part of gravity kind of pull it down, and if friction keep it up, so you get so steep, the gravity comes to friction. Force it on this diagonal, yes, and then the normal force now comes off the book like this at that point. But when just sitting there, if this table is level, then we draw nothing horizontal. Because friction only pops up if you have independent motion. Right now, there's no independent motion.
So you don't need it at all?
Nope. I was checking and it said you just need teachers.
We can't do it. Where are you going? Yeah, I wrote question mark 10 there.
Okay. I remember the day that I went to the math.
That one day with the math, that'll teach you.
I only went to that one day.
Control your bladder.
Thank you.
The manager is report to the main office. The manager is report to the main office.
Yep. Okay, I'll be on. We'll have like this. What happens if someone else's words? Because the center means like, I'll be a graduate member of